Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Yes, we've been on that series talking about salt analysis for the fast approaching WAEC SSC. Okay, we've looked at salt analysis before, but haven't looked at the various comments and sat down and tried to put the puzzles together. We've decided to look at a final revision for this exam so that everything just gels together and truly you can ace your exams. But before we move on, special appreciation to all those who have commented, who've liked, who've subscribed to this channel, especially on our last lecture video talking about salt analysis. We appreciate you. We're not taking that for granted. Okay, let's get into it. So talking about salt analysis, we're looking at a final revision. And on the final revision, recall that the salt this year, you're going to be given a salt C. And for this salt C is a mixture. This salt C is a mixture of two salts. Is a mixture. Actually, we're looking at sodium triazocarbonate 4 and lead triazonitrate 5. Of course, this looks like when these two, when they react, this is what we're going to. Ordinarily, when you have the solid sample, sodium triazonitrate and lead triazonitrate. Let's say, okay, this is lead triazonitrate, and let's say this is sodium triazonitrate. In the solid form, actually, we cannot have a reaction. So, but when we dissolve this in water, so that this and this, they are in aqueous form, that is when you can actually now talk of a reaction. Look at it again. When you talk, okay, in the solid state, if both will react in the solid state, then the reaction would have happened. But because the reaction will not take place, the ions will not be free, the ions will not be mobile. That is why there is no reaction occurring here, because this is in the solid state. But when you dissolve both in water, what you're going to have is a double displacement reaction, or what we call double decomposition or double dissociation reaction. So that what we're going to have is a case of sodium combining with the nitrate, so that we have sodium triazonitrate 5 and lead carbonates. Of course, all triazonitrates are soluble. So this is soluble. This will be soluble in water. This is going to be insoluble in water. This is soluble. This is soluble ordinarily, because all triazocarbonates are insoluble. But for the carbonate of sodium and potassium, they are soluble. So soluble, sodium carbonate is soluble, lead nitrate is soluble, and then we're going to end up in a test tube. When we dissolve both in when we add water, distilled water, we're going to end up with let's say this is the sample size of the salt in the test tube here. By the time you add water, the sample size that will be on the salt might just be something like this, not up to this again. So telling me that some of the solid here, some of the quantity of the salt are dissolved while some remain on the salt. Why am I saying this? Is because of the various questions that had popped up as a result of the last video, where someone had said, when we dissolve sodium carbonate and lead triazonitrates in water, that what we have is a precipitate. No, what we have is not a precipitate. As you can see on your screen, that particular comment, what you have when you dissolve both salt in water is not a precipitate. If you say this is a precipitate, then you'll be implicating yourself as a student, because for you to call this a precipitate, what it means is that what is supposed to be confidential, talking about what your sample is supposed to be for the exam. And that means you know, and that is why you know that it is a precipitate. Whenever you're being told to add water to a given sample, as far as chemistry or practical is concerned, or salt analysis, it is to test for solubility. It is to test whether the salt will dissolve or it will not dissolve. So we don't even talk of a precipitate here, because the real actual chemical reaction has not actually happened. So we don't talk of a precipitate there. That's the first caveat I'm going to be given. Then someone also said that sodium triazonitrate 5 is capable of decomposing if, when we eat this particular solution directly. Now, when we eat, that sodium triazonitrate is capable of decomposing into NaNO2, and in which case you're going to have oxygen. You know, someone said this, and that the person in the comment then said, okay, you're going to be asked to test for oxygen. I can tell you this is a capital no. It has never happened in the history of WAEC where you'll be told to test for oxygen. You know why? First, oxygen is odorless, it is colorless, it is tasteless, and then it is neutral to litmus. Then how are you going to test? The person said in the comment, he said you're going to use a glowing splint. I put it to you, and I'm 100% sure about this, that you can never be asked to test oxygen in the lab with a glowing splint. Take for example, in a lab where you have about 50 or 100 students and you're bringing a glowing splint, then WAEC is not careless to set you up to set the whole laboratory ablaze, because you're going to need the same lab for subsequent exams. So it's not possible, because this is too risky. That's why WAEC don't tell you to test for oxygen with a glowing splint. Of course, if you're going to test with a glowing splint, as you can see on your screen, then it means you're going to be talking about fire. And I can tell you, because of the danger there, you see a student dropping the fire on something that is combustible in the lab and setting everywhere ablaze. So it is not safe. And that way, I am pretty sure that the fact that WAEC has never asked this testing for oxygen, and the fact that it is neutral to litmus, it is odorless, it is colorless, it is tasteless, and trying to use a glowing splint as a confirmatory test for oxygen is something that comes with a lot of hazard in the laboratory, and WAEC will not do that, at least not at the SSC level. So I am pretty sure that you're not going to be told to test for oxygen. You can bin that, throw that in the bin. That is totally out of it. So what are the questions that we are going to be asked in this exam? Okay, that is going to pop up on your screen, and I can tell you that all of the questions that you're going to have in your exam come on Thursday, after putting into considerations the input of all those who had comments, and some other chemistry instructor who had reached out to me. That's why I've decided to put this final revision together. So what is your question exactly going to look like? What are the other adjustments that we've made to this new video that you're going to see now? So moving on, what should the question look like on a final note before your exam? As you can see on your screen, we were instructed here to put all of C in a boiling tube, add about 10 cm cube of distilled water, shake thoroughly, and filter, and keep both residue and filtrate. Now, knowing fully well that after the double decomposition reaction, or what you call double dissociation, what we ended up having was sodium triazonitrate 5 and lead triazocarbonate 4. We At that point, we knew quite well that this was soluble and this is insoluble. Merely looking at the way the form of the question, we were told to keep a residue and a filtrate. So I don't see here where the idea of a precipitate come in. For a student to come out and start talking about a precipitate, it simply means that the confidentiality of the sample is no longer there before the exam. So a student cannot be talking about the precipitate. Whenever we are told in chemistry to dissolve a sample in water, it is purely to test for solubility, and all a student is supposed to be concerned about at that point is this sample going to be soluble? Is it not going to be soluble? As you can see, there was a comment on that, and that comment is displaying on the screen. No, we cannot talk of a precipitate here. A chemical reaction has not actually occurred. We've not actually made use of a reagent per se. So we are just testing for solubility, trying to know what our filtrate is, trying to describe what our residue look like. That's just that. You cannot talk of the idea of a precipitate. Also, there was also another comment talking about why am I recording this as soluble and insoluble salts. I recorded this as soluble and insoluble salt. Well, just like I said, if this is my test tube, and let's say this is the size of the sample I had dissolved, I had put in the test tube before filling it up with my water. If after vigorously shaking together, this is the sample size I'm left with, not up to this, that tells me that some of the salt dissolved, some did not dissolve. So that tells me I have a mixture of soluble and insoluble salt. So this recording, as far as I'm concerned, is on point and is in line with standard procedure. You understand? So we clear on that. So we don't talk of the idea of a precipitate. Talking about the idea of a precipitate here is telling the examiner that maybe the sample actually has been reviewed, and you don't want to get yourself into losing up on valuable marks. So let's leave that. So the next question, as you can see on your screen, it says to about 2 cm cube of the filtrate. Normally, when you have dissolved your sample here, you're going to have a filter paper. When you pour your the mixture you have in your test tube here, the residue stays on the filter paper, while the filtrate here is our sodium triazonitrate 5. The residue is lead triazocarbonate 4. Why? All carbonates are insoluble in water except for sodium carbonate and potassium carbonate. So this here is soluble, this here is insoluble. So we were told to carry out this test on the filtrates, that we should add freshly prepared iron 2 tetraoxosulfate 6 followed by conc H2SO4. We've actually dealt with this in the last video. A link to that video is in the description of this lecture. So filtrate plus F3SO4 plus conc tetraoxosulfate 6 is going to give us brown ring between the layer of the mixture and the conc H2SO4. So that way triazonitrate ion is confirmed. Next question, question 3. This is talking about the residue. We were told to divide the residue into 2 portions. We were told to eat for 3 Roman figure 1. We were told to eat the first portion strongly in a test tube. Of course, when we eat the residue, that's what is on the surface of the filter paper. When we eat the residue, what we're going to have is a colorless, odorless gas. Normally, when we are told to eat any substance, usually we are meant to look out for any gas evolved or liberated. So in this case, residue plus heat, colorless, odorless gas is evolved. which turns blue litmus red. And of course, confirmatory test for carbon dioxide, which turns lime water milky. Of course, that's when it's brought in contact with lime water, it turns it milky. The fact that the blue litmus turned red, that tells us that's an acidic gas. And the fact that the gas turns lime water milky, that is telling you that that is CO2 gas from thiazocarbonate 4 ion. That's talking about 3 Roman figure 1. Look at the question again. Here we were told that we should divide the residue into 2 portions. To the first portion, we should eat strongly. That is because they expect that a gas here is going to be involved. Look at the reaction PbCO3. That's what we have. So what we're going to have here is going to be lead oxide plus carbon dioxide gas. Now, let's move to the leftover, the residue. A yellow residue when hot, which turns white when cold. Now, as a student, am I supposed to tell them I have a residue here and the residue is lead oxide? No, I am. It is not right for me to indicate that lead oxide is going to be that residue, because lead oxide is not the only solid. It's not the only residue that when hot it is yellow, but when cold it is white. Zinc oxide does exactly the same. Zinc oxide and lead oxide, they exhibit the same feature here. When hot, they are yellow, but when cold, they turn white. So it is not right for me. Recording lead oxide here is still a student showing the examiner that, look, I have been told about the sample. This is totally supposed to be confidential. It's about confidentiality. You're not supposed to even know your sample, what your sample is. You're not supposed to know that. So you cannot come here and tell us the residue is lead oxide. How did you know the residue is lead oxide? This is not a confirmatory test. So you have just indicated in your observation that, well, I saw a yellow residue when hot, which turns white when cold. And that's just about it. You cannot confirm 100% if it's lead oxide. What lead oxide exhibits here, zinc oxide also exhibits. So that ends question 3.1. And I hope I answered the question of the person who commented on restating what the residue is. No, you cannot do that. If you do that, that will mean you're in for something serious. You'll be losing out on valuable mark. No, you have to feign and play along as though you don't know the sample. You're just performing the experiment. That is what WAEC practical is all about. It's not just about you writing what you ought not to write. So moving on to the next question, 3 Roman figure 2, it says, to the second portion, talking about the residue. Recall we're told to divide the residue into 2, but it said to the second portion, add dilute nitric acid. Now, the thing is this: anytime we have a residue first because that there is a particular substance that is not soluble in water. So in that way, water is already out of the equation. So these are the substances we use when water cannot dissolve. Then this is the second. This is already arranged in the right order. When water cannot dissolve a sample, then the next possible thing we have to move to is dilute HCl and then cork HCl. We believe that these acids, both in the dilute and in the conc form, should be able to dissolve the solid. And in dissolving the solid, it must not form another insoluble solid. Take, for example, in the case of our residue, because we know that our residue is lead thiazocarbonate 4. Imagine lead thiazocarbonate 4. We already knew that lead cannot dissolve in water. So if we are adding an acid to a residue, to a solid that cannot dissolve in water, the aim is to dissolve that solid without the formation of an insoluble product. In the case of lead carbonate with HCl, this is what we're going to have. Lead carbonate plus HCl, we're going to have lead 2 chloride, PbCl2, plus H2O plus CO2. We all know here that lead 2 chloride is insoluble. So using HCl, when we are talking about the residue and we are to add an acid there, using HCl would have given us something insoluble. So that's one of the oversight. That's one of the mistake in the earlier lecture video. A very big thanks to one of the those who comment, although we've cited that before, as talking about at Estorial Media, as you can see on your screen. He highlighted that for us, and although we noticed that also before, but we decided that okay, in the final video we're going to make corrections to that. So we cannot use HCl to dissolve the residue because we are going to end up with another insoluble substance. So that's why we cannot do that. But when we say lead carbonate plus HNO3, look at what we're going to have. It's going to be, this is going to give us lead plus the nitrate, Pb2 plus NO3 minus, that's univalent, so I need 2 here. So I have Pb NO3 2. Now this is soluble, and then I'm going to have H2O and of course carbon dioxide. So you can see lead triazonitrate 5. This here is soluble. Then that way we can proceed with our then that way we can proceed with our test. And in this case, we have to then talk about, okay, the carbon dioxide involved. So when it comes to identifying carbon dioxide, it could be the residue plus heat, since lead carbonate can be decomposed on heating. And we're going to be looking at CO2 from CO32 minus. If you're not told to heat the residue directly, in identifying carbon dioxide, you can also be told residue plus HNO3. But take note, I've explained why we cannot use HCl. It is going to be nitric acid, dilute nitric acid. So residue will dissolve to give a colorless solution, and of course, we proceed with what we usually write as our observation when we are identifying carbon dioxide: colorless, odorless gas evolved, which turns blue litmus red and turns lime water milky. Gas is acidic because it turns blue litmus red. CO2 gas from CO32 minus. Why? There is a confirmatory test for CO2 here. It turns lime water milky. So that explains that. Okay, moving on to the next question. That's talking about 3 Roman figure 3. Of course, the solution we had when we, dissolved the residue with dilute nitric acid, we were told to divide that particular solution, resulting solution, into 3 portions. To the first portion, we were told to test with sodium hydroxide. To the second portion, we were told to test with ammonia solution. Yes, to one of the portion, the solution we had in Roman figure 2, if we add sodium hydroxide in drops and in excess, what we're going to have is a white gelatinous, or you say jelly-like precipitate. I've had comments, from the last video, someone saying no, it's not gelatinous, it's a chalky precipitate. Instead of the dilly-dallying, I think the best thing is to just say white precipitate, which is soluble in excess sodium hydroxide. That's another best way to put it. What you have observed is a white precipitate, and that particular precipitate will dissolve when we add excess sodium hydroxide. If that be the case with sodium hydroxide, what we infer is zinc or aluminum or lead 2 ion suspected, or you say present. Of course, in 3 Roman figure 4, we were told to then test with ammonia, aqueous ammonia. Now, solution in Roman figure 2, where we are dissolved the residue with acid, plus ammonia, aqueous ammonia in drops, and then in excess, white gelatinous precipitate insoluble in essence. You see, this time around it ended up as being insoluble in essence. But in the case of zinc, for zinc for zinc 2 ion, zinc 2 ion will still be soluble. That is why zinc is off when we use aqueous ammonia. So but in the case of lead and aluminum, both precipitates will not be soluble in essence. So since when we tested with aqueous ammonia, we ended up with precipitate which was not soluble in excess aqueous ammonia, lead or aluminum suspected here. So the big question then is, how are we going to be able to determine which of the cation that is present in this situation? Is it lead? Is it aluminum? And that is what question 5 seeks to answer. A very big thank you to someone who also raised that in the comment. Although we use the potassium heptazoldichromate 7 or potassium iodide talking about getting a yellow precipitate, but because the person, people talked about that in the comments, so we've decided to reiterate certain things on how we can confirm lead 2 ion, or if it's going to be lead 2 ion, or if it's going to be aluminum 3 ion. So moving on to the next question, 3 Roman figure 5. We were told to a portion of the mixture, that's talking about the solution we had in 2. The solution we had in 2, we were told to add potassium heptazoldichromate 6 or potassium iodide. Just like we said in the last lecture video, since ammonia cannot separate between lead and aluminum, when we use K2Cr2O7 or potassium iodide, a heavy yellow precipitate confirms lead 2 ion. But of course, when based on comments, if for the same solution you added dilute HCl, let's look at it. We had lead nitrate here. We have lead nitrate. We have lead triazonitrate 5. Okay, let me put that here. We have lead triazonitrate 5. If we had HCl, something is already clear. We're going to end up with PbCl2, which in itself is what a chalky precipitate is all about. Lead 2 chloride, that is your chalky precipitate. Not when you use your sodium hydroxide and then ammonia. No, you don't have a chalky precipitate then. But when you use HCl, because you're going to get lead 2 chloride, that is when you talk about a chalky, white chalky precipitate. Instead of getting yourself confused there, it's just better to have written for sodium hydroxide and aqueous ammonia. It's just better to have written white precipitate if you don't want to write gelatinous precipitate, white precipitate soluble in excess, white precipitate insoluble in excess. So that's what happens, and you can confirm that if you check your WAEC past question 2008 question 2D2. That way lead 2 ion is going to be confirmed. And with that, we've come to the end of everything that has to do with salt analysis for this year WAEC practical. Thank you all. We clocked 1,000 subscribers today. We couldn't have done it without you. Thank you for all of the comments, for cheering us on, for the good messages, for the encouragement. It's not been easy, but with you we've been able to go the whole length of the road. I appreciate that, and I can tell you that everything we've done today, your question in the exam cannot go out of what we have on the board, and everything we've touched on today, your question can just not go out of it. So that's going to be that about that. From myself and the entire team at 300 plus, it is bye for now.